Related to cost distance is path distance. We could start to think, well, this simple model of just slope wasn't sufficient. So it's probably not the only factor. And one thing to keep in mind about DEMs is that the slope doesn't calculate the actual distance traveled. So here's an example. We have a car, and the car is going up a hill. The horizontal distance, which we get just from cell size, is less than the hypotenuse of a right angled triangle. So the base distance or horizontal distance that the car travels between A and B on a slope is more than the horizontal distance would measure. And basically what we've been doing with cost distance is just considering horizontal distance and not considering the actual distance traversed. So we might want to minimize the actual distance traversed as well as the slope to have a more efficient path from B to A or A to B. To do that, we use, instead of cost distance, path distance. Path distance is another function in the cost distance toolset that takes into account the true geographic distance traveled as a function of varying slope on the terrain. And it takes in the same arguments as we saw for cost distance. So we have our start point, our cost, but also a digital elevation model, which makes sense to us. But for other types of path distance measurements, the DEM can be any surface. It doesn't have to be elevation. It could be a surface representing, some other dimension of cost, whatever that might be. In our case, it's very intuitive here because we're working with slope. So if we look at path distance from our start point, which is A, and then from B to A, we can see, well, how does that differ? Well, this is what we find here now. So again, the red line here is the path distance from B back to A. And we can see with path distance, taking into account also the true geographic distance traveled as a function of slope, that steep slope here, remember this is the area of a very steep slope right there, is avoided completely because the cost and slope, the actual distance traveled here, is more than going around it like that. And then it gets back onto the same path as it was before. So you can see how that varies. So just adding that, taking into account the true surface distance, does modify the least cost path. What about other considerations? We could take into account things like water. So avoiding water is probably pretty important when creating a trail. Why? Well, unless it's a very small stream, you have to build some sort of infrastructure to get over the water in order to have a trail. There could also be other things like outcrops. So there might be large rock outcrops that we might want to avoid as well for some reason. So we can start to add other cost variables into our analysis, like avoiding water or avoiding outcrops. And we just have to give certain values to water. So water, for example, should be avoided maximally. So we might give it a value of 100, let's say. So if we give water a very large cost, then the path will take into account that large cost even for a small little traversal and probably go around the water altogether to get from B to A. And that's because the water would have such a high cost compared to slope or actual distance, for example. And that's what we see here basically in this second one. So from B to A, taking into account water with a very high cost of 100 means avoid that as much as possible. And outcrops as well having that high cost. Then going from B to A, since there's water in here and there's an outcrop, it's going to avoid that completely. And that's what it does here. So certainly that's even further from the other solutions, which were much more closer to Trail 24. And so that tells us that going in this direction, at least with that type of cost for water and that type of cost associated with outcrops, doesn't make sense. in terms of whoever designed this trail. So we'd have to then start thinking of other things. And it's kind of an iterative process, as you can see. You can add more variables, take some away, check the path. And you could potentially, if you know enough about Python and how to program with it, is what we do. We do that in the 4th year course, learning how to create our own programs. You could do all of this and automate the whole thing with a number of different variables to swap in and out, and have some index such as the distance, from between the predicted path and the actual path, and just have the computer keep doing it until it minimizes that distance with a certain set of variables. So here, for example, just showing the addition of a third junction, B. We want to find from C to A. Well, that's the blue line that goes then into a green line here, with a different set of variables. Just for an example here, just to show you how we can easily add in other junctions or other points. So we can put both junctions in as destinations, C and B, and find the best single path from each back to the source. I could add other ones in to find where they might be as well. So once we have our cost weighted distance surface, we can test all kinds of scenarios. To undertake a least cost corridor, you can see here I'm using my t-cost from the cost path analysis, the least cost path that we did in the previous example. And as well, I have my junction B at the top and junction A at the bottom. And all we need to compute for the least cost corridor is the cost distance surface with A as the source, and a second cost distance surface with B here as the source. And then both of those cost distance surfaces go into the corridor function or tool. So going back to Python here, I already have everything imported and the environment set from the previous examples. So all I need to do here is get my cost distance surfaces. So in the first case, I'll say cost from B to A equals cost distance. And then here, I'll use A, the bottommost point, which is called source. And then t-cost as the cost surface. That's the cost surface that integrates, as you see here, the percent rise and slope with lakes. Next, I get the cost from A to B. So cost from A to B, and that will be cost distance with the from point, which is point B, as the source of the computation for least accumulative distance, and then t-cost again. Finally, to create the corridor, I first have to create a corridor layer. So okay, I'll call this cost corridor. And well, maybe I won't call it that, but I'll call it LC corridor equals corridor, and then the two cost distance rasters, cost from B to A, and then cost from A to B. Now we can have a look at that surface. I'll just close my Python window temporarily. And here we have the least cost corridor surface. So if I click here, for example, it gives me a value of 5,228 cost units. And that is the value along a least cost path between A and B. If I click over here, that value is 6,811. That is also a cell along the least cost path between A and B. So no matter where I click, the cell value represents the cost to go from that location to A and B. In other words, it's a cell traversed by the least cost path from A to B. Going back to my Python window, I want to create a corridor. So I might say, let's have a look at a corridor where the total cumulative cost of any path between A and B is less than or equal to 6,000 total cost units. So I'll call this core 1 equals Now we just have a relational statement, LC corridor less than or equal to 6,000. That produces a Boolean layer with 0 and 1. So I'm going to make 0 no color and just have 1 as green. So this green area represents the least cost corridor between A and B under the condition that no cost path can exceed 6,000 cost units. And here our cost units are just 0 to 100, so they don't mean anything. But you could think of this in other contexts, such as, for certain types of mammals to get through the landscape. You might have cost measures measured in kilocalories or something like that per unit distance. Just find out if there is a connectivity between two locations for movement of that animal. So this is just one example of a general least cost corridor between two locations. And so every cell within that corridor has a least cost path between the 2 points that does not exceed 6,000. And that's least cost corridor analysis.